In this section we study polynomial functions, and we focus on how to graph a polynomial. And we will focus on how to get information about polynomial functions by looking at the formula of the function or the rule of the function. And from that rule we can obtain some information about the behavior of the function at and around zeros of that polynomial, and the end behavior of the polynomial. I mean the behavior at infinity, positive infinity and negative infinity. So we try to collect as many information as possible and then graph the function depending on these information. So let's start with the general form of polynomial functions. Polynomial function is any function that can be written in this form, and where n is where a sub n minus 1 up to a1, a sub 1, a sub 0 or a node. All these are coefficients, I mean constants. And n, this n is the degree of the polynomial. This is the largest value n is, or the largest power of the variable x is the degree. And n, all the powers should be non-negative integers, as we discussed in a previous video. Now the first term, the first term, a sub n x to the power n, is called the leading term. The leading term. And this term plays a crucial role in graphing functions, polynomial functions. So this almost tells everything about end behavior of the function, of the polynomial. Now polynomials have domain negative infinity to infinity, and they are continuous and smooth functions. Now by looking at this general form of the function, we can study the end behavior. So let me summarize the information that can be obtained from the leading term of a polynomial. I'm gonna construct this table. Here a sub n, the leading coefficient, I mean here, and we have n, which is the power or the degree of the polynomial. Now the degree can be either even or odd. And a sub n can be greater than 0. I mean the leading coefficient can be positive or negative. Now this table should determine the end behavior of a polynomial. Now if n is even and the leading coefficient is greater than 0, that means the graph looks like this. And this means that as x goes to plus or minus infinity, I mean here, as x goes to plus infinity or minus infinity, what happens to the graph of the function? The graph goes to positive infinity from both sides. So f of x, the graph goes to plus infinity. And I draw some dots, or some dots here. That means the behavior here, the behavior of the function can be determined by studying the zeros and other things. So here we are just describing the end behavior, so we don't know in this stage much more about the behavior of the function here around zeros of that polynomial, but we know the behavior of the function at the ends of the function or the graph of the function. Now if if n is even and the leading coefficient is negative, then we have this graph. The end behavior looks like this. As x goes to plus or minus infinity, f of x, the graph goes to negative infinity. As you can see, the graph goes to negative infinity here. Now, if n is odd and the leading coefficient is positive, then the graph looks like this. The end behavior looks like this. As you can see, as x goes to positive infinity, what happens to the graph? The graph goes to infinity. So as x goes to positive infinity, the graph of x goes to infinity, as you can see here. And as x goes to negative infinity, what happens to the graph? The graph goes to negative infinity. Now, if the degree is odd and the leading coefficient is negative, then we have this behavior. Which means that as x goes to plus infinity, the graph goes to negative infinity. And as x goes to negative infinity, the graph goes to positive infinity. So this is the end behavior. You need to remember this. When it's even, then at the end, the function goes in the same direction, either to positive infinity or to negative infinity from both sides, depending on the leading coefficient. If it's odd, the degree is odd, I mean power 3, power 5, and so then we have the following. We have this behavior. On one side the graph goes to infinity, and on the other side the graph goes to negative infinity. So keeping this in mind, we can use this in graphing polynomials. But before that, let's discuss some ideas about the graph of a function in general. If we have this function x to the 5th minus 2, this is a polynomial, and the degree is 5. In order to graph this, as we learned before, to graph this function, we need to graph the basic function. Now the basic function is x to the 5th. So x to the 5th is this function. It looks like this. This is x to the 5th. And then subtracting 2 from this means it's translated 2 units down. So x to the 5th minus 2 looks like this. So we have shift down 2 steps or 2 units. But we have same in behavior. As you can see, the power is odd, n is 5, it's odd, and the leading coefficient is 1. So a sub n is 1, it's greater than 0. When n is even, when n is odd, and a sub n is positive, then the graph looks like this. And as you can see, we have this behavior. If the power is even, for example, if we have f of x equals x plus 1 all raised to power 6, here the graph is the same as what is the basic function. The basic function is x to the 6th. This is basic function. So when we graph this basic function, the graph looks like this. So this is x to the 6th. Now when we add 1 to the variable, not to the whole function, not here, but to the variable, that means we make translation one step to the left, to the opposite side. So when we add 1 to x, then we have this translated the graph one step to the left. So the graph may look like this. And here, as you can see, x has power 6 and the coefficient is 1, the leading coefficient is 1. So n is even, it's 6, and a sub n is 1, which is greater than 0. If the power is, or the degree is even, and the a sub n is positive, then the graph looks like this. As you can see, the end behavior is described here. It goes to positive infinity from both sides. Now let's talk about behavior of 0. Before we start graphing polynomials, we need to know something about the behavior at zeros. Now if x minus a raised to the power m is a factor of the polynomial f of x, I mean by factor, for example, f of x equals x minus 1 to the power 2 times x plus 3, for example, we could write the polynomial in this form, in this compact form, in terms of its factors. And as you can see, this is x minus a raised to the power, for example, 2 here, and here x plus 3 raised to the power, or raised to the power 1. So this is an example of a polynomial. If this is a factor, then we have two cases here. Now m is called, now if m is odd, m is called, in both cases, is called multiplicity of the zero x equals a, because x equals a, this is the value of x that makes the expression equal to 0. So x equals a is a 0 of multiplicity m. The repetition or the multiplicity is m. That means, for example, if we have x minus 1 squared, that means this is x minus 1 times x minus 1. That means the 0, 1, x equals 1 is repeated twice. Okay, now if m is odd, then the graph of the polynomial crosses the x-axis. I mean by cross the x-axis, if this is the x-axis and this is a, now the graph x equals a, the graph cross the x-axis at this point. I mean either this way or this way. So the graph crosses the x-axis. Or now if m is even, then the graph of the polynomial f of x just touches and rebounds, touches the x-axis and rebounds. That means the graph may look like this. At x equals a, the graph touches the x-axis and rebounds, but it doesn't cross the x-axis, or this way. These are very important things to keep in mind. Now let's take an example. For example, if f of x, the polynomial, can be written in this form, negative x, this compact form. This is equivalent to this form, but sometimes we can write the function in terms of its factors, and after factoring this or expanding this, we got that general form. So if we could write f of x as negative x plus 2 times x plus 1 to the power 2 times x minus 1 to the power 3, then we notice that in terms of the zeros, what are the zeros? The zeros are, what is the zero of this? What is the value of x that makes this equal to 0? X equals negative 2. What is the zero of this? X equals negative 1. What is the zero of x minus 1? It's x equals 1. Now what about the multiplicity? Multiplicity m. Here for this 0, multiplicity is equal to 1 because the power here is 1. For this 0, the multiplicity is 2. And for this 0, the multiplicity is 3. So we have here odd multiplicity, even multiplicity, and here odd multiplicity. Now how the graph looks like at the zeros. So at negative 2 here, at negative 1, at 1, the graph looks like this. Since the multiplicity is odd, then the graph crosses the x-axis, either this or this. So it crosses the x-axis, Now if the multiplicity is even, the graph just touches the x-axis and rebounds this way or this way. If it's odd, then we have same situation here. Good. Now what about the leading term? The leading term is how to find the leading term. We have negative sign here. This is negative sign. Now from the first factor we have x raised to the power the multiplicity 1, and from the second factor we have x raised to multiplicity 2, and from the third factor x is raised to the power 3 or multiplicity 3, and then we multiply them. We get x to the power. When we multiply, we add the powers, so we have power 6. So this is the leading term, and this determines everything. So here a sub n is equal to 1, negative 1, it's negative, and n equals 6, and that's even. If n is even, and the leading coefficient is negative, then the graph looks like this. The graph goes to negative infinity from both sides. Now that means if we graph the function, we know that we have x-intercept. What are the x-intercepts? Let's graph this function. What are the zeros? X-intercepts are the zeros. The zeros are negative 2, negative 1, and 1. Negative 2, negative 1, and 1. And what is the y-intercept? For y-intercept, we can determine it here. It's very easy. Y-intercept, we set x equals 0. When x equals 0, y is equal to, now just substitute x equals 0 here. You get negative 0 plus 2, 0 plus 1 squared times 0 minus 1 cubed, and that is equal to 2. So y equals 2 is here. Now the end behavior is, as we can see, the end behavior looks like this. So the graph looks like this from here and from here. Now at negative 2, the graph crosses the x-axis because the multiplicity is odd, so it crosses. But we want to determine one more thing. We can study also the sign of f of x. I mean to make a sign chart and determine the zeros. The zeros are -2, -1, and 1. And we can choose some test values, like for example we can choose 2 here, we can choose 0 between -1 and 1, we can choose -3/2, and we can choose -3 here. And we study the sign by substituting 2, for example, into the function. This function, we get here 2 plus 2 is 4, and we have negative sign out there, and 2 plus 1 is 3, 2 minus 1 is 1. As we can see, we have negative value here. Similar thing for a -3, we get negative here. When we substitute -3/2, we get positive. When we substitute 0, we get positive. Now, keeping this in mind, we understand this way. If the sign is negative, that means the graph is below the x-axis. If it's positive, it's above the x-axis. So for when x is greater than 1 here, the graph is negative, I mean below the x-axis. As we can see here, it's below the x-axis, and it's below x-axis here as well, because for values less than -2, it's below the x-axis. Between -2 and -1, the graph is positive, that means above the x-axis. And then we return to the other zero. The other zero is -1, but the multiplicity here for -1 is even. That means the graph just touches the x-axis and rebounds. And then from -1 to 1, the graph is positive, that means above the x-axis. We need to go back to the y-intercept and then come back to the other zero, 1, and 1 has multiplicity 3, which is even. That means the graph crosses the x-axis here. So this should give us a rough graph of the polynomial function f of x. This is how we graph polynomials if we are given the formula for that polynomial, or if it can be written as a product of the factors. Okay, now let's take another example. If we want to graph the function f of x equals 2x cubed plus 5x squared minus x minus 6, then we want to first find the zeros and multiplicity. So in order to do so, we need to find, so what are the zeros, multiplicity, and y-intercept. So in this case, we need to use the possible rational zero theorem. So the rational zero theorem says that all possible zeros are, we look at the constant term. So the factors of the constant term -6 are, what are the factors, what are the number that can be divided by can be divisors of -6, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. What about the 2, the leading term? So the factors are plus minus 1 and plus minus 2. And then we try to find the ratio. So factors of -6 over factors of the leading term, or the leading coefficient 2. And this means we need to find, for example, divide plus minus 1 by plus minus 1, and that's plus minus 1. Divide plus minus 1 by plus minus 2 is plus minus 1/2. And then for the second term, we have plus, or the second factor, plus minus 2 divided by plus minus 1 is plus minus 2. Plus minus 2 divided by plus minus 2 is just plus minus 1. And plus minus 3 divided by 1 by plus minus 1 is just plus minus 3. Divided by 2 plus minus 3/2. Now plus minus 6 is plus divided by 1 plus minus 6 divided by 2 plus minus 3, but we already have it here. So these are all possible zeros of the polynomial. I mean by possible zeros, there can be zeros. Some of them can be zeros, but not all of them are zeros, because we know that the degree of the polynomial is 3. That means we have at most 3 zeros. We can't have 4 zeros or 5 zeros, because the degree determines the maximum number of zeros. So these are just possible zeros, and the actual zeros are some of them. So we try some values. Let's try positive 1. Let's start with positive 1. Now, how to determine if this is a 0? There are 2 ways to do so, and actually the most powerful method is the synthetic division. Now, how to do synthetic division? We draw this table and we put the 0. We want to try just positive 1 here. We put the 0 here, positive 1, and then we put the coefficients of the polynomial. The coefficients are 2 is the coefficient of x cubed, 5 is the coefficient of x squared, -1 is the coefficient of x, and -6 is the constant term. And please pay attention here. If we don't have x here, if we don't have -x, then we put 0 for the coefficient of x. If we miss any power, any degree, we put 0 for that, the coefficient. Now we start with the first coefficient. We bring it down here without any changes, and then we, from below to above, we multiply. I mean, 2 times 1, we multiply by the 0, we get 2, and then we put it here under the 5, and then we add to 5 to get 7, and then we do similar step. We multiply 7 by 1, which is 7, put it here, and then add it to 1, we get 8, and then multiply this by 1, the 0, we get 8 plus negative, we have 8 here, we have 2, 7, and then we multiply, this is -1. This is -1. So 7 minus 1 is 6. So this should be 6. 6 times 1 is 6, plus -6 is 0. So if the answer is 0, if the last number gives 0 in the table, that means x minus 1 is a divisor. So x minus 1 is a divisor. And now what's left here? So we want to write the function in terms of its factors. So x minus 1, x minus the 0 is 1. X minus 1 is a divisor. Now the rest of the polynomial or the other factor is, now we start with this. This is 2, but we subtract 1 from the power. The power was, or the degree was 3. This becomes the coefficient of x squared. If this is, the power is 5, then we subtract 1. This becomes x to the power 4, and so on. Now the second one will be the coefficient of x, and then 6 is the constant term. So we have this factorization. Now we can factor more by looking at this. This expression can be simplified. We can factor this, and we learned some method in class. There are different methods to factor this type of quadratic functions, but one of the powerful methods is the following. You have 2x squared, so we write 2x over 2, and then we try to find two numbers where the multiplication is a times c. A is 2 and c is 6, 12, and the sum is the middle term. The middle term is 7. What are the two numbers whose multiplication gives 12 and the sum is 7? The numbers are 4 and 3, and the sign is plus. And then we try to simplify to get rid of the 2 in the denominator. So this can be written as 2 times x plus 2, and then we can cancel 2 with 2, so we get x plus 2 times 2x plus 3. So we can put this here to get the function f of x written in terms of its factors. Now these factors are linear. As you can see, the power of x is 1, so we don't need to simplify, or we can't simplify more. So we could write the function in terms of its factors. Then we determine the zeros. What are the zeros? The zero of this is x equals positive 1. The zero of this is x equals negative 2. The zero of this is x equals negative 3/2. These are the zeros. What are the multiplicities? The multiplicity here is 1, the power is 1, and the multiplicity here is 1, the multiplicity here is 1. So the multiplicity is 1 for all these zeros. And then we find the y-intercept, or the leading term is given. So the leading term from the original function has 2x cubed. So a sub 3, because the degree is 3, n is 3, a sub 3 is equal to 2, is greater than 0, and n is 3, that's odd. So the graph from the table looks like this. So this is the end behavior. This gives us the end behavior. Now we can find also the y-intercept. What is the y-intercept? We just set x equals 0. That gives, now when we substitute x equals 0 either here or here, because those are equivalent forms, let's substitute it here. This is 0, this is 0, this is 0, and we get negative 6. So it's negative 6. Y equals negative 6. So 0, negative 6 is the y-intercept. Now we can graph. We have the sufficient information about the graph, about the function, so we can graph it. So let's start with the x-intercepts, which they are represented by the zeros. The zeros are x1 equals 1, x equals negative 2, x equals negative 3/2. So x equals negative 2 and x equals negative 3/2 here, and x equals positive 1. These are the x-intercepts. And then we determine the multiplicities. As we can see, the multiplicities are already determined. Before we continue, we want to graph sign chart for f of x. We put the zeros. The zeros are negative 2, negative 3/2, and positive 1. And if we test some values like positive 2 here, we get positive 0 between negative 3/2 and 1. We get negative, because if you substitute 0 here, you get 0 minus 1, negative 1. 0 plus 2, positive 2. 0 plus 3 is 3. That's less than 0, negative. So that's why we have negative here. And then we continue from between negative 2 and negative 3/2. It's positive if we choose some value here. And if we choose a value less than negative 2, we get negative. So that means the graph is below the x-axis here, above the x-axis here, below, above. Now, keeping this in mind, now we can graph the function. So we remember that the end behavior looks like this. So we start from here, and from here, this is the end behavior. And then between these points, we have at negative 2, the multiplicity is 1 for all cases. That means that the graph intersects the x-axis at each of these points. That means the graph crosses. Now between 1 and negative 3/2, the graph is below the x-axis, but we need to determine the y-intercept as well. The y-intercept is this point here. It's 0, negative 6. So the graph should continue to this point. I mean, I can graph it this way. The graph looks like this. Intersects the x-axis, and then we go back to the other 0, -3/2, and the graph intersects the x-axis here and go above and then back to -2, because between -2 and -3/2 it's positive, it's above the x-axis, but then we return to x equals -2, and to the left of the -2 the function is below the x-axis. This is the graph of f of x, or rough graph of f of x. So in order to graph a polynomial, we need, if we can write it as in the factor form, then we can find the zeros, the multiplicities, and the y-intercept, and find sign chart that can help us determine whether the function is above the x-axis or below the x-axis, and we can determine the end behavior from the leading term. Now let's take another example. If we want to graph the function f of x equals -x minus 1 times x minus 3 times x plus 2 to the power 2. Now in this case we are given the function written in the factor as factors, product of factors of the function. So we determine the zeros. The zeros are x equals 1, x equals 3, and x equals -2, and then we determine multiplicities. I mean m equals 1 here, m equals 1 here because the powers are 1. Here the multiplicity is 2 at x equals -2. And then we can determine the y-intercept. The y-intercept, we set x equals 0, we get -0 minus 1 times 0 minus 3 times 0 plus 2 to the power 2, and that gives us -1 times -3 times 4. So we have -12. So the y-intercept is 0, -12. This is the y-intercept. Now we can determine the leading term. So the leading term can be determined this way. We have negative here, and then x to the power 1. So we just choose x from each parentheses with the multiplicity. It's the multiplicity of the 0. So x here raised to the power 1, and then x raised to the power 2, the last parentheses. So this is -x to the power 4. And this determines the end behavior. The a sub 4 is -1 and n is 4. That means since the power is even, it's either open up or open down. But since it's the leading coefficient is negative, it's open down. So this is the end behavior. Now we study the sign. We make a sign chart of f of x. So we put the zeros. The zeros are 1, 3, and -2. And then we choose some test values like 4 here, 2 here, 0 here, and -3. If we substitute 4 here, we get, for example, if we substitute 4, we get -4 minus 1 is 3, 4 minus 3 is 1, 4 plus 2 is 6 squared, and that's negative. We don't need to worry about the value, but we need to worry about the sign. And similarly, we get positive here, negative here, and negative here. And as you can see, since -2 has even multiplicity, we expect to have same sign around it, either negative or positive, because we have even multiplicity. Now we have all the information that we need, so we can graph this polynomial. We determine the zeros. The zeros are -2, 1, and 3. And the in behavior looks like this. Okay, now we determine we know that negative, let's start from the right. 3 has multiplicity, x equals 3 has multiplicity 1, so the graph crosses the x-axis, and as we can see, after between 1 and 3, the function is above the x-axis, the graph is above the x-axis, and then we go back to the other 0, 1, x equals 1 has multiplicity 1, so the graph crosses the x-axis. And we need to determine the y-intercept. The y-intercept is 0, negative 12. So 0, negative 12 is somewhere here. So this is negative 12. The graph continues to negative 12. And then we go back to the other 0, negative 2. But we notice that negative 2 has multiplicity 2. That means the graph touches and rebounds at this point. So this is the graph of the function f of x. Now we have some terminology here. We have some terminology. F is a polynomial with x-intercept C0, then we call x equals 0, x equals c, 0 of the function, so we can call it 0, or we can call it a solution of the equation f of x equals 0. So we use solution with equation form, and we use 0 with the function form f of x, and x minus c is a factor of the function. So these are just terminology that can help us determine, help us to understand what do we mean by 0, solution, and factor. Now we have the intermediate value theorem. After graphing these functions, we need to know something about the functions or the zeros of the functions. So we have a very powerful theorem that's called intermediate value theorem. This theorem says that if f of x is a polynomial with real factors or real coefficients, I mean the a's are real, defined on, for example, on AB, in this interval, where f of A and f of B have opposite signs, then the result is there exists at least one zero or one real zero between of the function between A and B. So this guarantees the existence of a zero between A and B. Let's take an example. For example, if we have the function, the polynomial x squared plus x minus 2, and we want to define it on defined on 0, 2, we want to show that f of x has a 0 between 0 and 2. So we want to show that there is a 0 between 0 and 2. In this case, what we need to do is to test f of a and f of 2 and see if they have opposite signs. So f of 0 is, just substitute 0 here, you get negative 2. This is less than 0. F of 2 is 2 squared is 4 plus 2 6 minus 2 is 4. It's greater than 0. So f of 0 and f of 2 have opposite signs, and that means there exists, so by the intermediate value theorem, IVT, there exists E0 between x equals 0 and x equals 4. We have, and that means the graph will intersect the x-axis at some point between 0 and 2. So this theorem is very powerful in determining whether there exists a 0 or not. So we are trying to get as many information as possible from the function. Now the last theorem here is the boundedness theorem. The boundedness theorem says that if you have a polynomial with degree n greater than or equal to 1, f polynomial with degree n is greater than or equal to 1, the real coefficient and positive leading coefficient, then and f of x is divided by x minus c, then we have two cases. If c is greater than 0 and all numbers in the bottom row of the synthetic division alternate in sign, then the result is that f of x has no 0 less than x equals c, or less than c. And if that means this is a bound of the zeros, so there is no 0 less than c, that means it's lower bound. X equals c is a lower bound. Now if c is less than 0 and all numbers in the bottom row of the synthetic division table or Plato, then if c is greater than, I need to change this sign. If this is less than 0, this is greater than 0. If c is greater than 0 and all numbers in the last row are non-negative, then the result is f of x has no 0 greater than c. That means it's an upper bound. That's why we call it boundedness theorem, because it determines the upper bound and the lower bound of zeros. And all these theorems are given just to determine as many information as, or to give as many information as possible of the zeros, because sometimes we don't know anything about the zeros and we need to use some numeric methods to find these zeros, and that's not easy job. So we can at least say something about the zeros. Here we can, for example, if c is less than 0 and all numbers in the last row of that synthetic division table, then those values are, for example, alternate. Here, this is the keyword here. Then that gives us the lower bound of zeros. If c is greater than 0 and all values are non-negative, then we don't have 0 greater than c, so that means upper bound. Let's take an example. We want to show that the function f of x equals 2x to the fourth minus 5x cubed plus 3x plus 1 has for the function. Okay, so the real, let me write here, show that the real zeros of the function, this function a have no real zero greater than 3. So 3 here is C. This is C. So here we need first to do the synthetic division and divide by 3 and put the coefficients of the polynomial with their signs. So we have 2, -5, but we don't have x squared, so we put 0 here, and then 3, we have 1 here, and then we bring this down here, we multiply it by 3, we get 3 here, and then add it to -5. 2 times 3 is 6, -5 is 1, and then we multiply by 3 again to get 3 plus 0 is 3, multiplied by 3, the 0, that gives 9, plus 3 is 12, multiplied by 3, you get 36, added to 1, we get 37. Now if we look at the numbers here in the last row, we have non-negative. C is greater than 0. So C is greater than 0. That means this case. And all numbers are non-negative. As you can see, all of them are non-negative. So we can say that, yes, there is no number greater than, no zero greater than C equals 0. There is no zero greater than 3. Now part B, if we want to show that no real zero less than -1. Now this is C. This is C. It's less than 0. Less than 0, so we need to apply this. We need to see if they are alternate their signs. So we do the synthetic division again here, but we divide by -1. We have 2, -5, 0, 3, 1, and we bring this down here, times -1, we get -2, -5, -7, and then we multiply by -1, we get 7 plus 0 is 7 times -1, we get -7 plus 3 is -4, and then multiply by -1, we get +4 plus 1 is 5. Now if we look at the signs of the numbers in the last row, we have positive, negative, positive, negative, positive. So they are, we have alternate, the signs are all alternate, or are alternate in sign. So that means the two conditions are satisfied, and that means there is no zero less than -1.